Okay, in this example, we have a rolling disk, which is basically moving towards right. We know the magnitude of the velocity of point C, which is on this disk, and we want to find the velocities of point B and D. Now, uh, when we have a rolling disk, if there is no slipping, if there is no slipping between the disk and the floor, the point that the disk is in contact with the floor uh, has the same velocity as the floor. Again, if there is no slipping. So when imagine when you're driving your car in a road and it's raining. So your tire has there is some slipping between your the car's wheels and the road, tires and the road. Now, if there is no slipping, so we are just driving, let's say on a totally dry road, a perfect road. If there is no slipping between a rolling object, in this case the disk, and the floor that that object is basically moving on or it's rolling on, the velocity of that point, the contact point, and here we're talking about the velocity of point B, which is the contact point, is the same as the velocity of whatever it is in contact with. Remember, if we're talking about gears and two gears, the contact point had the same velocity. So imagine that this floor is the second gear. There's no slipping between this one and the other one. So they have the same velocity at their contact point. Since the velocity of the floor is zero, so the velocity of point B is also zero. So I'll just write it here, and this is a general rule. So if there is no slipping, there is, if there is no slipping, I would say between the disk and the floor, the velocity of contact point of the contact point is zero. Now here it says it's rolling, so rolling with no slipping, meaning that there is no slipping basically, and the velocity of point B would be zero. So we get VB is equal to zero. That's it. Now let's figure out what is the velocity of point D. Point D. Now we know the velocity at point C. Well, we know its magnitude. You want to know what is the velocity of point D. Well, global coordinate frame is already there. I'm just gonna, as always, change it to uppercase so it's not confusing. I'm gonna put my local coordinate frame, right? I gave you a rule of thumb that put your local coordinate frame where you have the most information. I'm gonna add something to it. So either put it on a point that you have the most information about that point, or put it on another point and study the point that you have the most information about it. So two possibilities. In the previous example, we were talking about a piston and cylinder moving, a piston moving inside the cylinder. You could put the global local frame, your local frame, either on point. Well, I put it on point C, but you could put it on point B and study point C. You can just do it as a practice, and you can you'll get the same result. You can find the angular velocity of the link AB in previous example. Now again, let's get back here. So we have, what I'm going to do is that I'm going to put my local coordinate frame on point B, right here, and I'm going to use that to study point C. Right? So I'm studying the point that I have the most information about. So this is X, and this is Y. Now I put the frame there, Now the second decision was to which object I want to connect this frame to. Well, in this case, I'm going to connect it, attach it to the disk. So it's the local frame is on point B and it's attached to disk on point B. Now let's write the equations. The equation for velocity. I have VC. I'm studying the point I have information about. Is equal to VB plus V relative plus omega cross R. Okay. Well, VB, I just told you that we talked about it, that is 0, so this is gone. V relative, well, the relative velocity between C and B, well, I attach the frame to a disk, so the frame is moving with the disk, which means that if I freeze this local frame, C doesn't move. In other words, B and C are moving together, so this term is also 0. There you go. The only thing left is just VC and omega cross R. Now I know what is the magnitude of VC, so let's just look at the magnitudes and don't even bother looking at the vectors. So let's say I want to know, well, I'm just going to equal to make magnitudes equal. So VC is equal to, I'll put it this way, R omega. And R is what? R is the distance between here. R is the distance or the position vector for point C in, this would be R, in local coordinate frame. So looking at this, plugging in the numbers, I'm only looking at the magnitudes because that's all I need. I know omega cross R, the direction, and basically I just have one equation, and I can just use that to find, and I can just focus on the magnitude of these values. Let's see what we get from there. From there, I know the magnitude of VC is 5. The R, well, R is this length. Looking at this right triangle, R is the square root of 0.6 squared plus 0.6 squared. Okay. So I'll write it this way. Square root of 0.6 squared plus 0.6 squared. Multiply that by omega. So I can actually find omega, or the angular velocity of the frame about its origin. That would be 5.89 rad per second. There. Now, once we know omega, the rest is relatively straightforward. So we want to find the velocity of point D. Now let's focus on point D. We use the point we had the most information from to get the angular velocity. Now let's focus on point D, and I'm studying this point now. I'm going from B, using the same frame, pretty much everything is the same, but now this is my R. Fix it. Now this is my R. So, I changed R to this value now for the rest of the calculation. Now let's write the equation for point D. VD is equal to VB plus V relative plus omega cross R. Now, same story, VB is still 0. There is no V relative because both are attached to the same rigid body, the frame and the point we're studying. So we'll get VB as, well, VD, I forgot to put vector signs, these are all vectors. VD is equal to omega cross R. Let's find what is the, well, for omega VD, for omega cross R, I know omega, I know R, so I can basically find the magnitude. So I know the magnitude. I can also find the direction. I know the direction. This is omega. Here. This is omega. Once this is omega, this is omega r, I'll get omega cross r in this direction, perpendicular to r. Omega cross r, we talked about this term before, is always perpendicular to r. So omega cross r is perpendicular. Maybe I should have done a better job trying the perpendicular line. I guess this is a little better. It's perpendicular to r. So this angle is 90 degrees. So this would be omega cross r. So I know its direction and I know its magnitude. So I can find, well, about d, I don't know anything. This vector, I'm going to draw the vector here, looking at omega cross r. What is omega cross r? Omega cross r as a vector. Omega cross r, we have this vector which is omega cross r. Well, we'll look at this, consider this as the horizontal line there, and this one is the angle I'm looking for. So I can actually decompose this omega cross r in x and y direction. Now that angle is equal to this angle. What is this angle? Look at this triangle there. This triangle here. We have 0.6, 0.6, and then this length. Well, first, before that, let's find r. We'll see if we can find r. So r is, well, whatever we have in this length. Let's look at this right triangle there. This right triangle here. It's a right triangle there. So I know this length is 0.6 plus 0.6 cosine 45 degrees. Right, this length. And then this length is basically just 0.6 sine 45 degrees. And write it this way. So r here. R would be square root of, let me see if I can explain it better. So this is the right triangle, or you can either look at this right triangle, whichever you feel more comfortable looking at, or it's easier to see for you. So this length is equal to square root of this length, square root of this length squared plus this length is squared as part of this right triangle. This length is 0.6 plus 0.6 cosine 45 degrees. This is 45 degrees. Cosine 45 degrees. And this length is just 0.6, this hypotenuse in this triangle, sine 45 degrees. So I'll write it this way. It would be 0.6 plus 0.6 cosine 45 degrees squared plus 0.6 sine 45 degrees squared. You know the r, omega, well, let me move this a little bit. Move it here, so it's not on the way. We found omega, right? Now we have to find what is the direction of omega cross r. Omega cross r is a vector. We have to find its components in x and y direction. So to do that, let's look, let me clean up this part a little bit. We don't need this. And this. We don't need that either. So it helps probably to see things better. Okay, so in this case, I'm looking for this angle, which is equal to this angle. Now this angle, what is that? This angle, again, looking at this right triangle, you can actually find this angle, which is basically tan inverse of this length over this length. the same values. Tan inverse of 0.6 plus 0.6 cosine 45, well, tan inverse of 0.6 sine 45 over 0.6 plus 0.6 cosine 45. So this angle, if I call it theta, theta is basically tan inverse. What is, well, this is also theta. I'm looking at this triangle. It's tan inverse 0.6 sine 45 divided by 0.6 plus 0.6 cosine 45 degree. You can calculate that, you'll get the angle of 22.5 degrees. Now, which means this is omega cross r. If this is horizontal, omega cross r is this vector, and that vector exaggerated the angle, creates an angle of 22.5 degrees. So I can actually write it in terms of the components. That would be equal to this way would be r omega cosine 22.5 degree in I direction plus sine 22.5 degree in J direction. I also have to write the answer for this R. The R value, if you do this calculation, you will get 1 point, move these, so there's a little bit of more room there. Just going to fit it here. That would be 1.1806, or the other way around. That would be 1.1086. You plug in these values, so VD here, VD as a vector becomes R omega. Well, R, I know it's 1.1086 times omega, which is 5.89. I found it from before. And then cosine 22.5 I plus sine 22.5 J. This gives you VD as a vector is 6.032 I plus 2.498 J. That would be the velocity of point D. We already found the velocity of point B. So these are what we were asked to find.